Industrial hardware deployed in harsh environments degrades. Security fences exposed to aggressive coastal climates or persistent solar radiation develop microfissures, allowing oxidation to breach the surface and rapidly compromise the metallic integrity. This displays a critical complaint lodged with A1 Manufacturing. 75 security fence panels installed at a Middle East project site began corroding within 6 months. A failure in the field triggers an immediate, high-stakes root cause analysis across the entire manufacturing pipeline. Management must isolate the exact origin point, identify the raw material supplier, the specific purchase order, the machine, the operator on shift, the galvanizing and coating parameters, and calibration certificates from that day. Pulling this specific thread through disparate records requires several days of manual cross-referencing by quality engineers. A multi-day delay stalls operations and leaves compromised hardware in the field. The inability to rapidly isolate a defect turns a localized material failure into a compounding liability. Modern shop floors capture a massive volume of information. Every physical action, batch movement, and machine cycle is logged. A1 Manufacturing possesses all the information required to solve the corrosion failure. The problem is not a lack of data. The captured data is isolated into distinct silos, spread across ERP servers, isolated PDFs, and scattered email chains. These broken relationships create immense friction, forcing investigators to manually bridge gaps. TraceX compresses this manual dig into an automated workflow under 5 minutes. Solving the traceability crisis does not require installing new sensors to gather more data. It requires engineering a unified digital product genealogy to connect the records that already exist. Before any automated trace can occur, the physical manufacturing entities must be mapped into a standardized ontology. This product traceability matrix defines the relational logic. Every physical entity, from the supplier to the raw material batch, all the way to the finished product, is assigned a strict, unique ID. To avoid the prohibitive cost of replacing legacy ERP systems, TraceX extracts this master data through REST APIs, pulling the variables into a centralized traceability layer. On the shop floor, low-cost physical identifiers bridge the physical-digital divide. Scanning a barcode on an incoming steel coil generates a batch ID. That raw material ID automatically maps forward to the specific production order that consumes it. The linkage continues rigidly downstream, tying the production order directly to the exact machine and the specific operator logged into that shift. By enforcing this strict relational matrix, the physical chaos of the factory floor translates into a mathematically predictable, searchable graph. Legally required certifications and inspection reports hold vital quality metrics, but they remain useless if trapped as unstructured flat files. This material test certificate floating in isolation provides no actionable intelligence during a high-speed recall investigation. To function within the relational network, every PDF must be injected with structured metadata, including a specific document ID, version control, and current status. Assigning an entity ID allows an isolated document, like a daily calibration certificate, to permanently anchor to a specific machine node. Until every piece of quality documentation is converted into a relational entity, end-to-end traceability is structurally impossible. Consider a highly critical scenario where a severe metallurgical anomaly is positively confirmed deep within the raw material supply chain. The system instantly logs a red alert, identifying the compromised material as batch RM2026-XXX. TraceX bypasses manual tracing, quickly executing an algorithmic graph traversal to locate all associated data linked to that singular batch. The traversal moves immediately downstream, mapping from the defective batch directly into the specific production orders that consumed it. It cascades through the galvanizing and coating phases, isolating exactly which finished product nodes carry the defect. The algorithm finalizes the trace by identifying the exact external shipments and specific customer sites that received the compromised panels. An investigation that previously required cross-referencing multiple systems over several days is now solved mathematically in just a few moments. This architectural precision transforms a chaotic investigative panic into a controlled, immediate corrective and preventative action workflow, blocking affected inventory before it causes further damage. There is a prevalent misconception in the industry that simply pointing an artificial intelligence at a lake of unstructured ERP records will resolve quality assurance issues. Large language models cannot be trusted with unstructured defect data. When asked to parse raw, disconnected records, they have a high propensity for hallucination, inventing false relationships where none exist. This split architecture is mandatory for regulated environments. The deterministic Postgres database on the left must remain the immutable source of truth. On the right, the TraceX Copilot operates in a strictly delimited role, acting solely as a natural language query interface. When queried, the Copilot retrieves hard evidence directly from the database, translating the complex graph traversal into clear, readable text for the user. Enterprise AI does not invent intelligence or find missing data. It simply accelerates the user's ability to interrogate a perfectly engineered relational graph. This complete network graph represents the practical application of the system, consolidating disparate records into a single product genealogy. This foundational logic establishes a clear Industry 4.0 roadmap. The platform scales from low-cost ERP integrations today, extending smoothly toward advanced sensor inputs and predictive analytics. Because the underlying relational matrix is mathematically sound, it natively accepts high-fidelity IoT and RFID data when the organization is ready to deploy it. Organizations do not need to wait for advanced robotics to achieve digital maturity. They can build a highly effective intelligence layer immediately using existing tools. Technological scalability relies on the integrity of the underlying data structure, not the complexity of the hardware collecting it. Total system visibility enables high operational awareness across the entire supply chain, identifying bottlenecks and defects at the moment they occur. The failure of a physical component in harsh environmental conditions may be inevitable, but the failure to understand why it happened is an architectural choice. Speed and quality assurance and recall intelligence is not achieved by gathering more data. Speed is achieved by meticulously engineering the connections between the data you already possess, enabling traceability in under 5 minutes. It is time to stop hoarding unstructured records and start building connected, resilient digital genealogies.